Hi, hello, this is Jenny. So today's topic is digital electronics. Yeah. So what we should know about this digital electronics? Digital electronics is the backbone of modern electronic devices. Okay. So we are using all the electrical devices in our home, organization, as well as public places, right? So in this digital electronics, how they made. Okay, so here you can see this is the processor. Okay, so right now our computer system all are using this processor. Without this processor we can't do any work in our system. So that hardware type, how they are making, like this information we are going to see in this session. Okay, let's move. Okay, so this is your electronic circuit board. Okay, so here you can see, so the users, the people, the technicians, they solve the problems. Okay, so these are the diodes, okay, transistors, and here you can see this integrated circuits. Okay, so IC means integrated circuits. So integrated circuits, here you can see 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 bit means 1 byte. Okay, so this is also one of the 8-bit transistor. Okay, and then you can see 4-bit transistors. So this electronic circuits made by transistors, okay, diodes, registers, flip-flops, logical circuits. Okay, and finally we can made this chip. Okay, that means integrated circuits. Previous years, second generation, they developed this integrated circuits. Right now we are reducing or redeveloped by the transistors. That means integrated circuits. Right now we are using chip, microprocessor. Okay, so control everything on the system. So this is the best example for this digital electronic circuits made by this elements. Okay, and next, this is your MC, MP. MP means microprocessor. Okay, here you can see almost 16 or 32 bits. Okay, integrated circuits. And next, here the data transmitted through this circuits. These are the logical circuits. Okay, here we are going to see what is flip-flops, gates. Okay, see here you can see this gates, circuits. Okay, logically we are going to make everything in this board, that is circuit board, digital methodology. Okay, so digital electronics means here we can communicate and store our information by using of this flip-flops, registers, gates. Okay, gates means here we can use three types of gates. And okay, so simply we can put this and, or, okay, and not. Okay, so like this gates we can use Boolean algebras. Okay, so these are called Boolean algebras. Okay, algebra. So this digital circuit made by this components. Okay, so without this components we can't work in our system. So digital circuit board is the backbone of digital electronic devices. Okay, so where can we use this digital electronics? That applications are healthcare system, telecommunication system, and government official system, even television, system, media, network, Wi-Fi connection, we are using this digital, and digital clocks. Okay, so whenever seeing the timing in a digital watch, clock, smartphones, laptops, desktops, so each and every digital electronic devices we are using this type of digital applications. Okay, so digital applications all are making by this logic circuits. Okay, so in this logic circuits, if we want to make means, I should know about what are the gates, what is integrated circuits, what is diode, what is transistors, what are the flip-flops. Okay, so what are the registers, how it will work, then only I can connect the circuits and then communicate with the systems. Okay, not only in communicate, we are going to transmit our data with the help of this boards, circuit boards, and then we can store our information in that chip. Okay, microprocessor, we can store our information and retrieve the information. So that's the reason we are full and full concentrate on this digital electronics, because nowadays we are making all the information in a digital manner. Okay, here you can see this example. So in previous years they were used analog signals. Okay, right now also we are using analog signals, but now in the digital electronics means we are using this type of signals. Here you can see zeros and ones. This is discrete methodology. Okay, discrete means we are going to transmit our data by using of zeros and ones. That means here on, off mode. Okay, here we are having two switches in digital methodology. Digital electronics means we are having two switches. One is on mode, another one is off. At analog system, we don't have two switch type. Okay, so continuously it's moving. This is on wave signals. Here we can transmit data like a waves. Okay, you can see or you can imagine how the ocean. Okay, so how it is there, the ocean waves we can see. So we can't stop the ocean or waves. Continuously it's coming, but no one can stop the waves, right? So the same methodology in analog signals, that is infinitive, non-stop, continuously it's working. There is no interval time, there is no break. Okay, but in digital system we are putting some finite statements or finite algorithms. Okay, that is zeros and ones. You should take this type of this time you should take this type of rest, you should give this breakable, or you should give some break, then after that you can do your work. So like this we are putting some intervals in our digital signals, but analog signals continuously we are passing the data. Okay, so one by one we are transmit the data. Main difference is in analog signals we can get lot of disturbance or noise. Okay, pollution, but in digital signals we can reduce that noise pollution as well as that disturbances. Okay, so when we pass our signals or transmit our data, we couldn't get that disturbance quickly. So that is the difference between analog signals as well as digital signals, right? So best example I can say, right now I am speaking with you through this media. So that is one of the analog signals. When I speak these words from my mouth, okay, so it opens or it comes through my mouth. That is analog signals. Continuously it's coming. That is wave signals. Okay, but digital signals means if I give some breaks. Okay, hi, bye. Okay, next. So like this, if I give some break or interval period of time, that is digital signals. Okay, so here you can see how it works. Two switch modes. So when my signal is go up, that is on position. If it goes down, that is off position. Here up is on, off, on, off. Okay, So wave method, here we can apply in this analog. Digital, you can apply zeros and ones, switch mode. Okay, so right now all the digital electronic devices, they are using this type of methodology, not analog system. Okay, and next, so that is also example for your understanding how the digital signals is passing our information from one device to another device. Okay, so here you can see there is no information. Now the information sends packets. Here you can see the network concept also, packets. Okay, so now the data is sending all the informations in a packets methodology. Okay, so right here there is no information. Yes, here information. So if it is information, means that is on position. If there is no information, means that is off position. Okay, simply we can say this is high, this is low. When I raise my voice, that is high pitch. When I lower my voice, that is low pitch. So when like this, we are passing our signals, high pitch and low pitch. Okay, so in two ways we can pass, but if you are taking digital devices, digital electronics, means we are passing the information in a discrete methodology, that is zeros and ones, right? And next, another, this is for your understanding. Okay, analog signals means here you can see the signals transmit the data like a waveforms, and digital signals, it transmitting the data zeros and ones, that is high and low. Okay. Another example for your understanding, what is digital electronic circuit. So in this circuit, this is integrated IC, integrated circuit. So here you can see 8 bits. 8 bits is equal to 1 byte. Okay, so 1 byte. So here you can see this omega notation. Okay, so why we are using in this part, if we are coming down, my data information is low. Okay, when we pass high, means that voltage is high. So here my voltage is low, here my voltage is high. So in this methodology, we can pass our signals by positive and negative manner. Positive means high, negative means low. Okay, and next, so in this digital circuits, we are going to perform lots of complex, that means mathematical programs we are going to perform. Okay, so real-time examples we can see. Before that, we should know how we can store our numbers in the digital circuits. Okay, see here commonly we are focusing the 4 number system. Okay, the categories are decimal, binary, octal, hexadecimal. Okay, so decimal base is 10, binary base is 2, octal base is 8, and hexadecimal base is 16. Okay, so these are known as radix also. Okay, so this number system calculations we are going to see in our digital electronics. Next, so I am going to do all the calculations in this categories, but I want to know how to convert this number system from one decimal to one part to another part. For example, if I am taking decimal number system, means I am going to convert that decimal to other number systems. Then only that logical circuits it will perform, and it will produce the output to the user what they expect. Okay, and next, binary to other number system, we can convert octal to other number system, as well as hexadecimal to other number system we can convert. Okay, and here you can see the chart. So in digital electronics, the number system is the basic foundation. Okay, so number system means we can split in 4 categories. First one is decimal, binary, octal, and hexadecimal. So already I said decimal base is 10, binary base is 2, octal base is 8, and then hexadecimal base is 16. 16 means 0 to 9 we are using numbers. after 10 to 15 we can put some alphabets. Okay, that is hexadecimal conversion. So first one is, here you can see, this is the example for decimal to hexadecimal conversion. Okay, or here you can see, okay, now first one is decimal to binary. Okay, then we can move to octal and hexadecimal. Okay, so this is the example for decimal. Decimal means ordinary number, whole number. So that number is going to convert in that binary conversion. Okay, so if you want to convert binary conversion means we should use the basis 2, because where we are going to convert, we are going to convert in the binary methodology. So binary means we should use that basis 2. So they given some numbers, for example 243. Here you can see the 243, they divided by 2, right? Yes. So when we divide by 2, you can get one remainder. Okay, another one remainder. If there is no remainder means you can get 0, right? So at last you can get this digit, but you should write from the bottom to top methodology. So how can I write this? Here you can write 1 1. Okay, so from right to left we should write. Okay, but we should take the values from bottom to top. 1 1 0 0 1 1. What is the base? Because here we are seeing binary, that's why I am using the radix, the base is 2. Okay, so this is the best example for decimal to binary conversion. Another example I show you for your understanding. Okay, here we can take number 52. Okay, 52 or 59, let's take, this is for your conversion. This is your decimal number. Now I am going to convert in a binary methodology. Okay, so binary means I should use 2, right? Okay, so now we divide. Again 2 2s are remaining 1 2, 7 2s are 2 2s are 3 2s are 6, remaining 1. Okay, and 3 you can divide. So the answer is 1 1 1 0 1. Okay, so the 59 decimal value, that is base 10, the binary value is 111 0 1, base value is 2. Okay, this is your binary conversion. Okay, so next let's move on another example. Okay, so if you want to again get back this number, we can split this divider into 4 bits. Okay, so next session I will tell. Okay, this is for your example. You can get this answer from decimal to binary conversion. And then next, this is for, okay, next one is decimal to octal conversion. Okay, so first we have seen decimal to binary conversion, and then decimal to octal conversion. We can take same number. Okay, so octal conversion means you should use the base 8. Okay, so when we divided by this digit, the octal number is 8 means you can get this answer. Okay, so if you divide by 8 you can get this answer. Okay, 3 8s are 24, and then 3 remainder. Okay, and then you can get this answer 363. So base is 8. So this is the example for decimal to octal conversion. Okay, and then decimal to hexadecimal conversion. Decimal to hexadecimal conversion, we can take the same digit. Here you can apply base is 16. Okay, so base is 16 means you can get this 1/16 are 20 on, okay, remaining 3, so you can get 15. So 15/16 are, you can get 241, remaining 3, 240, remaining 3 we can get. So the answer is 153 base 16. Okay, so here you can see the whole digit. Okay, decimal, octal, hexa. Okay, for example 5. If you want to binary means we should divide by 2. If we want to get octal means we should divide by 8. If you want hexadecimal value means we should divide by 16. Okay, so 16 is not possible. We can get this answer 165. 16 value is, we can get up to 15 value. Okay, that is F. So next digit is the same, 16 on 5, the base 16. Okay, so here you can get 85. Okay, and 2 we can get this remainder 1 and 1, so answer is 101. That is the binary value of 5. Okay, so like this we can do all the calculations in our logic circuits. Okay, by using of this flip-flops, registers as well as gates. Okay, in next session we can see other methods, other number system and their conversion. Okay, so thank you so much. Bye from Jenny.